All right, so we're doing angular kinematics again, and right now I'm looking at question 10.4. So we've got a wheel, it tells us the radius, it's rotating in the XZ plane. Ooh, this is kind of spicy. Let's enjoy this for what it is. Notice in this case, I hat is the direction kind of coming out of the page, and then J hat is to the right. Every once in a while, this shows up, and then Z would be K hat. So just so you've got it. All right. And determine the units. I think that part you could do on your own. So I'm going to skip part A. If you have trouble with it, you can send me a question later. But let's assume you could figure out the units on numbers by this point. And then according to the figure it right, what unit vector is implied on omega of t? So here's this disk. It's going to be rotating. I want you to think to yourself, omega is a vector. What should I put for the vector? I got to sneeze. Sorry about that. Okay. So if you had a second to think about it, what I wanted you to think was, again, grab that axis with your right hand. Fingers curl in the direction of rotation. So you might have thought either J hat or negative J hat. Here I'm going to assume J hat, right? So it's Y axis as drawn in this particular figure. Because I chose Y to the right, okay, so what? It's not I hat, it's still J hat. So I would say J hat. Okay. Ooh, we haven't had something like this yet. Determine the number of revolutions completed by the wheel. Oh boy, when it has maximum rotation rate in the positive direction. That's a dense looking sentence. You might remember some of these from chapter 2 when you had these very compact sentences that contained a lot of information. So let's go through this and try and think about this. Number of revolutions. Number of revolutions is asking for, think to yourself, what are they asking for? Delta theta. Delta theta is the amount of angle displaced. That's essentially how many times around it goes. That's the number of revolutions. So you're looking for how many radians, and then you're going to convert that to revolutions. At what time? Well, we're asked when it has max rotation rate in the positive direction. So when, whoops, not when omega equals a max. Okay. So how do I find the max and min of omega? I take d dt of omega, set it equal to 0, and then solve for t. And then we could use this, and then don't forget to do the second derivative test to make sure it's a positive. Sorry about that. And now it's getting pretty crazy. So I'm going to clear this out and go to the solution. So again, that's pretty intense. You got to know you're looking for delta theta from the word revolutions. You know, maximum rotation rate means basically figure out alpha, which is the derivative, not a alpha. Set alpha equal to 0 and solve for t. And let's go over there to the solution. Oops. All right. And somewhere down here. Oh boy. So what I did is I just got all the equations here, right? So obviously alpha is the easiest. Whoops, crap. This was given. That was given. And so what do you have to do? You have to take a derivative to go down this way, and you have to take an integral to go up to this one. And then since no initial angular position was given, I'm going to assume just like we usually assume x initial is 0 unless otherwise specified, if I don't give you a theta initial, you can assume theta initial is 0, okay? So typically, almost always, this is true, unless I specifically tell you otherwise, okay? All right, and then max RPMs will occur when that's 0, so you go through the math, and I think you go. And you could actually do this. Oh, yeah, okay, so let's walk through these words here. So here's what I did. Here's, I took the derivative, I set it equal to 0, and then I solved it for time. Okay. After that, then you could come into here and you could plug that number in and get omega max. Great. I can verify that with a second derivative. How do I know this? If I take two derivatives of omega, this term drops out and I get a negative number. That means the second derivative is negative. That means this is a maximum, not a minimum. Okay, that means it's a positive maximum. Okay, cool. Now, wait a minute. This didn't ask for max rotation rate. It asked for number of revolutions. So I got to take this time and shove it into there. And then you can get that. So it looks like it goes about that many radians, which is this many revolutions, which is about 0.2, about. That's a fifth of a turn. It rotates about 1/5 of a turn. Okay. The wheel reverses direction. If we go back to that one, the question for part D asked, at what time does it reverse direction? That is just set omega equal to 0. So if you set alpha equal to 0, you get a maximum omega. If you set omega equal to 0, you get the time it reverses direction. That's the time where it changes sign. All right. So I'm going to clear that. And if we keep going, if you want to get the net force, you could get A total. A total is this, both. Okay, so let me read what it says. At what time do points on the wheel experience 0 net force? So if you're talking about net force, that's a sign, hey, get A total. And in this case, either omega is 0 or alpha 0, but never both at the same time. So if you look at these plots, you could actually make these plots and see. At one of these times, or actually, we already did this work. We know at this time, alpha is equal to 0, but we still have omega. And we know that at this time, in part D, omega is equal to 0. And then you get some weird ass plot. Something you should know here, we cannot use our standard kinematics equations. So to be clear, whoops, these equations right here are no longer valid. This requires constant alpha. Constant alpha does not apply. Whoops. In this problem, omega is some function of time that's got t squared in it. That means that alpha is a function of time. That's what tells us do not use constant alpha. Well, I apologize, I didn't emphasize that enough at the beginning, but this time for questions on that. So yes. Okay, so this is a good time for questions on that. All right. Let me stop for a sec. Okay, so hopefully that made some sense. All the same problems we had in chapter 2, got to look out, can I use kinematics or not? Do I have to do my integration, or can I just use my standards? What about areas and on the plot? I have to think about that. And then we also have to distinguish between a tan, a total, a centripetal, and an alpha, which is angular acceleration. Okay. Look at question 10.5, really, 10.5 at the top of page 57. Just think to yourself, what tech is required? Don't do it. Just think, what technique will we use? obviously it's from chapter 2, right? Everything is on these 2 pages is from chapter. It's the same crap. Oh, I'll give you a second to think. And hopefully you thought separation of variables. So in this case, you want to use separation of variables for that. And I don't think I'm going to stick that on your test. So just letting you know, but hopefully you can see that those techniques are cool. So if you had to pick a problem pages to skip, I would say skip 10.5. All right. And since I'm the one writing your test, I should know whether or not it's on there. So, all right. I think I'll let you do 10.6, 6.5, and 6 3/4 on your own. We kind of did a bunch of these already, so I would like to move on. Those are the 3 that you could do on your own, and hopefully what we talked about will reduce your efforts outside. This is actually the next page is really fun, so let's do that one. I'm looking at page 58 right now, and I'm going to bring it up on, okay? This is one of the few fun pages we got in this book here. So, okay. What I want you to do is I want you to get stronger at relating these equations to their translational equivalent. So if you don't have the first 9 chapters down, this makes this part a lot harder. And so part of the reason I'm hammering you so much on the first 9 chapters is because if we have any hope of getting through chapter 10 in a reasonable manner, we need to start relying on an analogy that will make this dramatically faster. Whoops, looks like I forgot a paren on that. Whoops, my bad. Good thing it's not a code. All right, so it turns out have these new rotational equivalents. So if I could scroll down just a little bit. Okay, so X, we said that X is basically equivalent to theta. And remember, theta is not a vector in general, only if the axis of rotation doesn't change. So as long as we keep a fixed axis of rotation, this analogy is valid. So this is kind of the one special case. As long as the axis is fixed, we can use that. Velocity, omega. Acceleration, tangential acceleration, becomes alpha. So mass and moment of inertia is the new concept. That's like rotational mass. It's a measure of how big you are and how your mass is distributed. For example, figure skater with the arms in has a small moment of inertia, easy to rotate. Figure skater with arms out has a large moment of inertia. More on that soon. There's force. Okay, the equivalent would be torque. Torque is a lot trickier than force. We'll get into that. And then instead of regular momentum, we have angular momentum. And so these topics, torque and moment of inertia, will be the remainder of chapter 10. And that's the stuff that's on test 2, chapters 5 through 10. So we got to get through torque. And then chapter 11, angular momentum, is on the next test. All right. But if you want to, you could take a second and think about this. Well, if I know sum of forces is mass times acceleration, I could rewrite that as sum of torque, because force and torque are equivalent. And then instead of mass, I would use moment of inertia, rotational mass. And instead of acceleration, I would use angular acceleration. So take a second. You've got your book there. Take a second and fill out the rest of this page and see what you think. And the answers are in the solution manual. So I'm going to pause for just a second. Take a second and just try and get used to that and see if you can write down the equivalents. And try and be good with using the vectors when they're there and not using the vectors when they're not there. All right. So obviously some of these things are vector quantities, some are not. Just bringing them up on the page so you can see. We're trying to fill in the blanks on the rotational equivalent. And I tell you what, I'll take a look right now, and you can take a look and see if you got some of them. It's really hard to tell where you guys are at, so my apologies if I'm going too fast. And if you don't want to do that problem anymore, you could just look at the screen. All right. So force goes to torque. Mass goes to I, moment of inertia, this new concept that we begin on the next page. And A tangential, goes to alpha. You could actually rewrite this as, oh, crap. I just see a typo there. You see that? Clearly that's wrong, right? I forgot to change the torque over. So what is this? 10.7 solution. Line 2. Sum of force goes to sum of torque. So that should be a sum of torque equals this equation's also wrong, isn't it? Both of those are wrong. Oh my gosh, there's no M in that equation. Did I do that in the workbook too? Yeah, so clearly there's no M there. I was cutting and pasting and I was in such a hurry. I'll fix this up. So I tell you what, I'll go through and double check these tonight, but you can see that there's this kind of rotational equivalent. I think it's just the first one that I screwed up. So I think it's just that one. Yes, I'll check the chat. No M. No M. So yeah, and then so there's no I on the moment of inertia one. So both of those are wrong. Basically, take out the M, take out the I, and this should be a torque. I will fix that up tonight after class here. Sorry about that. That's a screw up. All right. Usually we do some of these in class, and so a lot of these screw ups never get noticed, right? All right, that's cool. All right. I guess maybe we'll look at one more of these. We've been talking about momentum. So this is going to be a huge thing. Angular momentum. That's going to be our last conservation law. We've talked about conservation of energy, conservation of momentum, and the last one will be conservation of angular momentum. And those are the big three conservation laws that make up first semester physics. So we're getting close to that. I have a whole section in chapter 11 kind of hammering that, our three conservation laws. This is one worth noting, I guess. Kinetic energy. This is called translational kinetic energy. So the T here stands for translational kinetic energy. And this kinetic energy rotational, or RKE, notice it's some sort of rotational mass and rotational speed. All right. So this one ends up being used a lot, and so does this one and this one. I'll get the chat. Very good questions here. Why is there no torque in the work equation constant force? So let me take a look. That's a good question. So remember that theta is like X. And so in this case, we could talk about work in three dimensions. So we would have X, Y, and Z, Fx. But when we're talking about rotations, I don't know if you remember, I said we're restricting ourselves to only one rotation axis. And that's why you could actually have theta X, torque X, theta Y, torque Y, etc. But because we only have one rotation axis, I dropped the subscript. So hopefully you could hear that, Sam. If so, let me know via text or via the chat or whatever the hell that is. All right. So because we only have rotations about one axis, I left off the subscript. Yep. Okay, cool. Good question. All right. So now let's go to page 59, at the top of page 59. All right. Top of page 59. Let's go back to here. And I think this sums it up. Moment of inertia is a world of hurt. You can't say it any more succinctly than that, people. Yeah, mass is pretty darn simple. You put something on a balance, you got it. You have a big mass, you have a large resistance to change in motion. Think about a train. The more mass you have, the harder it is to change your motion. A train has a large mass. It's hard to get it started, but once you get it started, it's hard to stop. Okay. Moment of inertia is similar to that. Okay. The more moment of inertia you have, the harder it is to get you started rotating or to stop your rotation. So, moment of inertia is a measure of your ability to resist changes in rotational motion. Let that sink in. So, there's a good question here. Let's see what it is here. Okay. You get an equation sheet. And to be honest, Jay, I'm almost thinking about letting you guys have open book, but then shortening the exam to 3.5 hours. So I'll talk to you more about that. I figured people would actually like being able to use their books. I may end up doing that, but if I do that, I'm definitely going to cut the time down by half hour. All right. So that's a good question, Jay. But right now, the exam will have an exam equation sheet. If you want to know what it looks like, it will be, you could look at yeah, this chart is on there. I already maxed out as it is XC. I don't know what that means. Okay. I don't know what you're saying, Luke. Oh, reverse cross product. Oh, okay. That's cool. All right. That's good. But yeah, you get 3 hours to take the test right now. And right now I gave you an hour to upload, but I don't think you need an hour after I'm seeing people getting that figured out. So I'll probably cut that down. But if I add in letting you use your book, that's cool. Anyways, worry about that next week. I'll figure that out after I do some work. All right, let's get to this. Moment of inertia it depends on 4 things. All right. Obviously, it depends on the amount of mass. The bigger mass you have, the harder it is to rotate. But it also depends on the shape. If I could look at this shape right here versus this shape right here. If you rotate with an axis through the center, it's going to have one value of 1/12 mass times the length squared. If you rotate it about the end, look, there's a different answer. So we see that how the mass is distributed matters. It matters. And tied in with that is both the axis location and the orientation. Take a look at this one. If you run an axis through the center of the disk, but it's perpendicular to the disk, you get a 1/2. If you run it through the center of the disk, but it's in the plane of the disk, you get a 1/4. So one of the things students have a heck of a time dealing with, just like this one, look at this. If I run this through the plate and it's in the plane of the plate, I get a 1/12. If I run it perpendicular to the plate, I get a 1/12, but it's a b squared plus a squared instead of just a b squared. We see that you get these, the formula that you grab to do a problem will depend on the amount of mass, the shape, the axis location, and the axis orientation. And there's no shorter way to say it. It depends on all 4 of those things. So you have to make sure you understand all 4 of those things before you use this table. And yes, you get this table and a couple extra. I forget which 2 extra I threw in there. I think it's the thick ring. So you can see here I have a thin ring. I think I throw in the thick ring too. All right. So watch out for that one. Good question in the chat here. That's correct. So if you have more I, or again, more moment of inertia, it's harder to change the rotation. And remember, it's harder to get started and it's also harder to stop. I like to think about a bicycle wheel. Look at these factors. So if I could go into this table here and address this, look at a solid disk. A solid disk has mass mr squared here at a factor 1/2 sitting out front, whereas a thin ring has this factor mr squared, but no 1/2. What this means is for the same amount of mass, a thin ring is harder to rotate than a disk. Okay, so if you take a disk and a thin ring and you put them on a track and let go of them, the thin ring will be slower to get going. It'll have smaller translational speed at the end of a race. All right. More on that when we get to some later chapters. Okay. Or sorry, some later problems in this chapter. Good question. Keep those questions coming if you've got them. All right. So I'm going to get us started here, and I want to try looking at 10.8. Normally, I do a demonstration with these things. And so what we're going to do is we've got two pipes. If you've ever seen me with these in class, oh, there's a question. Ryan, it's a trick question, and it turns out it doesn't matter. But more on that later. You wouldn't necessarily expect that. I'll get to that question in a minute. Okay, Ryan? All right. Yep. Okay, so I'm looking at 10.8. So here's what we want to do. In rod 1, there's 2 point masses, the gray disks, and notice it says for 10.8 and 9, treat the gray cylinders as point masses. Okay, we've got this radius. So the radius is 25 times smaller than the length. And the point masses are 5 times, each point mass is 5 times m. So the pipe itself is this kind of gray, or is this clear, it's the white pipe, and then that has mass m. Then you're going to add to it 2 point masses with 5 times the mass. And the idea here is, just like with center mass, we kind of added up the pieces. We're going to do that again. If I want the total moment of inertia, I'll get the moment of inertia of each piece and add them together. All right? And so if you had to take a guess, which one of these is going to be easier, rod 1 or rod 2? And I'll get the chat while you think about that. Okay, got it. Oh, these headphones get tiring after a while. Okay, I'm going to go into here. Axis rose. That's my attempt at humor. It's not good humor. All right, let's break this down. This is rod 1. Right here, what I did was I said, oh, I'm going to go to my chart. And I know that a thin rod with an axis through the center matches this one. This is a thin rod with an axis through the center, right? Thin rod, axis through the center. That's why I went up and I grabbed this 1/12. Now I'm going to come down here, a point mass. That's right here. A point mass is just that mass times its distance squared. So I'm going to go into my equation sheet. This was the rod. Okay. I had 2 point masses, each 5 times the mass, and they were each distance L/2 away. Going back to that picture, and then I'll come back and do this again. In this case, this distance right here is L/2. And this axis is right through the center. So then, and again, this is also L/2. So in the point mass formula, I'm going to use X equals L/2 for both of those in the point mass formula. So if you're looking up in your page, notice it says I of a point mass is mx squared. Okay. All right. And so if we go back, whoops, we got the rod, the 2 point masses, and then you add it up. By the way, if you're not good with fractions, you should either learn how to use fractions on your calculator or just get good at fractions. Okay, with this chapter and the next chapter, there's a massive amount of fractions. So if you're not good with fractions, get good at it, all right? And so in this case, notice this unusual thing right here. If they're both sitting at the center, X is equal to 0. And I'm going to go back to the other one and show you that just a second. So for rod 2, case 2, where was that? Rod 2, they're both sitting at the center, so that's why I set x equal to 0. Now you may be saying, wait a minute, dude, you're full of it. When they're at the center, they're not point masses, but yeah, I did say to treat them as point masses. If you look carefully, check this out. If you want to be a math snob about it, which I like being a math snob sometimes. Don't these look like two of these? If you really wanted to treat them and be a little bit more precise, you could actually do this. The thing is, look at this. Radius is L over 25. So when you square that thing out, you're going to get L squared over 25 squared. That's going to be pretty small. And that's why I ignored that term. That's why I think it's okay to treat them as point masses here. So I'm going to go back to the other one here. And I actually worked it out. If you want to see what it would look like, you could do it. All right. And it's less than a 5% correction. So I think it's reasonable. It's even more negligible for 10.9. So I think these are actually really good problems to do. And I think you would be crazy if you don't read these instructions and follow them closely and do these problems. And at the very end, what you could do is you could tabulate these things. And while this might seem silly, this can help get you an idea of which things should be easier to rotate. And before you look at the numbers, you could think about this. In all of these cases, think about which one of these cases should be the easiest to rotate. So you've got problem 10.8, 9, and 10. Just take a second and think. And if it helps, the easiest one to be rotated would be the one like the figure skater with the arms in. If the mass is close to the axis, it should be easy to change the rotation. So think about this. Which one out of all those has the mass close to the axis? I'll give you a second to think. These two. All the mass is pretty much right on the axis. Look at it. This one should have a very small moment of inertia. Now flip it. Which one should have the largest moment of inertia? Which one has the most mass far from the axis? It's not this one. It's probably not this one. It's probably going to be one of these three, right? And now let's think about it. I'm going to go to a new color. This one and this one are pretty similar, but in this one, the rod is farther away. So this green one down here should be slightly bigger than rod 1. And now, because in the point mass formula, you get this thing here where you say it's mx squared, it turns out this one is probably pretty huge. Because it's x squared, the distance matters. So I suspect this one is the largest, rod 1 in problem 10.9. And that might not be obvious to you. And that's why I said, maybe you should actually do this. And I see there's a question. I'm going to clear this out and get the question here. Okay. That is correct, Jay. Yeah. And so isn't that wild? These two shapes, even though the mass is distributed differently, have the same moment of inertia because it's distributed the same relative to the axis. These two disks are on the axis. These two disks are on the axis. This rod is on the axis. This rod is on the axis. That's cool. If you're into chemistry, this stuff matters in chemistry. There's a thing called rotational spectroscopy. And if you could think about this, I'm trying to foreshadow that in a strange way without telling you anything about it, which is obviously not the smartest move. But if you could think about this, Oh yeah. Oh, cool, Jay. Right on. Okay, so in this case, take a look. You could think of this as one molecule, and one atom, and this could be another atom, and this is a molecule. And if you ignore the mass of the rod, you could just view this as a dumbbell, and this would be a diatomic molecule. And the moment of inertia, it turns out, is really small when you put the axis of rotation parallel to the dumbbell. So if you had a molecule on axis, the rotational energy associated with this orientation is negligible in all your chemistry calculations. Okay. And so it turns out this matters, and there's another orientation that matters. That would be the axis coming out of the page, which I can't draw right now. So if you're doing rotational spectroscopy in an upper level chem class, this matters to you, this particular problem. So, oops, let me clear all those. Cool. All right. Right on. That said, take a look at those problems at home, and I'm going to go ahead and move on. So now, here's how you would do the calculus formula. Or if you want, you could think of this as point mass formula. We saw that our point mass formula, if I could write that on this page, is mass times x squared, right? Where x was the radius. So imagine if you had a bunch of point masses. You'd say this is xi, or maybe x1. Let me start over. Or well, let's not. Then maybe you'd have x2 times mass 2 plus ... and you could just keep adding up point masses. Well, that's the same thing as doing an integral. The total moment of inertia comes from adding up the distance from the axis for each slice. Now, this can get very, very sneaky in a hurry. For example, if you had a 3D object, you don't get a choice of how you slice it anymore. And so this is a case where slicing is actually perhaps, well, it's arguably just as good as doing 3D integrals. So if you're a 3D integral person, yeah, you could do this. Oh boy, nasty. But I'm going to just cut to the chase and show you down here, what do we need to do these problems? Okay, so from a practical standpoint, you could do these, and we're getting close on time. It's almost time to go. So let me just scroll down here, and I'll get to the chat in just a second. Whoa, crap. There we go. This is the table. If you see a problem, this tells you how to set it up, okay? And this is the practical integrals that you're going to do if you need to figure out the moment of inertia of a shape. And let me get that chat question here. Okay, Dane, I'll make sure I get your question afterwards. All right. Oh my goodness. All right. When you're doing these problems, let's take a look at this. You need to worry about the location of the axis, the size of the, oh my gosh, the density of the material. Is it uniform or is it non-uniform? So it's a lot like center of mass, except you don't get to choose your slices. You have to choose these slices, okay? There's some comments there. Let's just go look at a problem. So this one gets tricky, and I'm looking at the top of page 61. I know you're tired. I know you're ready to get out of here. Let's see if we can get 3 minutes into this problem and learn a couple of things about this. That way you could try and grind it out at home on your own. So 10.11. We have a rectangular plate. It has uniform density. Oh, I could read my screen too. The plate has length A and height B, whatever. Okay. Mass is M. And it says the plate is to be rotated about the y-axis, okay, shown. So notice that's going through what looks to me like the center of the plate. So let's just assume that's going through the center of the plate. Obviously, we know the answer is in the table, but our goal here is not to memorize an answer. It's to kind of understand this. So let's think about it for a minute. Which of those slices, do you want to use the horizontal slice or the vertical slice? And remember, it says in part A, which of these two slices gives the same value of R for every part in the slice? If we're going to do center of mass integrals, Sorry, I'm going to move the screen on you. I'm trying to do this integral. The trick is to use this integral, I'm going to slice it up, and every point in the slice has to have the same r, otherwise it doesn't make sense. That's why I had to use this screwball cylindrical slice here. But in general, all points in the slice have to be equidistant. So going back to this one, the horizontal slice is bad. Why? Because this chunk of the slice has a different radius than this chunk. This one's got a big radius. This one has a small radius. That's a bad idea. So when you're trying to get the y center of mass, or sorry, oh crap, I just misspoke. I'm tired too. When I'm trying to get this, look at this crazy result. We're going to have an x, and then this right here is going to be dx, right? And the output is going to be moment of inertia about the y-axis. So we get an x integral to get the y moment of inertia. This is exactly opposite the center of mass. If you're doing a center of mass integral, when you get a dx, you get an x center of mass. If you get a dy, you're doing a y center mass. But for moment of inertia, to get the vertical axis moment of inertia, you need a dx in the integral. Crazy. All right, so I'm going to clear this, go to the solution, and then we'll call it a day. So I'm looking at this. Let's figure out the mass density. Oh, mass density is just mass over area. Get the mass of the slice. Let's just get to the solution so you can get out of here. I guess this is what I usually do on the whiteboard, so this could use some help here, but it's the vertical slice of height A, and then sigma is mass over area. If you're trying to remember where I got this from, that was from chapter 9, page, just a second. I see there's a chat question. I'll get to you. If you're working on these chapter 10 problems, write down page 43 chart. So the chart on page 43 helps you with this crap. So if you go back to here and go way back to page 43, you could find it. All right. And let me check the chat. Okay. Okay, got it. All right. So yeah, let's go back to this one. You guys have got to be tired and ready to get out of here. DM, that a sigma, just like when we're doing center mass, it's going to be the area of the slice times the density of the slice in units of kilograms per meter. So if I could, remember that sigma is mass total over area total, all right? Which notice that's going to have units of kilograms per meter squared. If you haven't watched the center of mass videos I put up in the week 12 module, watch those and this will help a lot. I talk about all this stuff in the center of mass videos I put online in the Canvas website. But we see that here, I can get this result, I can get this, I can crank this out. And now it's just plug in, do the math, and we get the result. I'm gonna, yeah. Let me go back to one other thing. I know it's time to go, but I'm gonna show you one other thing. If you go back to this one, notice the main difference here is the axis has changed. And so if the axis changed, you're going to get different limits. All right. So this was the old integral, and then you'll see the limits change. So I'm going to call that good, and I'm going to stop the live stream now. All right. And if you want, you could stick around and ask questions or take